Welcome to the first issue in the FastScan application campaign series. This is Johannes Kind and I'm the Senior Application Scientist responsible for the FastScan system. Today's FastScan application is thermally induced polymer film de-wetting, a dynamics application. Dynamics experiments, especially for irreversible processes, need an external trigger, so that the dynamic process being observed happens while, not before the AFM can record it. External triggers can, for example, be chemical, addition of a reagent, optical, light, environmental, like gas or moisture, or, like in this experiment, thermal. The sample is a piece of silicon wafer, chemically treated with a hydrophobic layer and a thin polystyrene film on top. Typically, the sample is prepared by spin coating. The hydrophobic treatment of the silicon and the molecular weight and thickness of the polystyrene can be varied to explore different de-wetting phenomena. Wetting phenomena can be found in many industrial and everyday situations. Lubrication of surfaces, like in cars and car engines, the cornea in the eye, or paint. Like most of us will know from experience, paint will only stick to a surface that has been properly cleaned and prepared, and that is oil-free. If there are oily spots on the surface, what happens is that there will be holes in the paint. The paint de-wets. The forces driving wetting and de-wetting are the effective interface potentials between the fluid and the substrate, and between the fluid and air. For a homogeneous fluid layer to de-wet, the symmetry of the layer must first be broken. 3 mechanisms are possible. Which one occurs depends on the driving forces, the polymer's molecular weight, and the layer thickness. The possibilities are spinodal de-wetting, thermal nucleation, and heterogeneous nucleation, as you can see in the pictures taken from a publication by Ralf Seemann et al. And this is actually the collaborating group that we have worked with to create this data. In the experiment, polystyrene films of less than 100 nanometer thickness, and in our case much less than that, on hydrophobically treated silicon surfaces are good model systems to study de-wetting. They can be prepared under contaminant-free, clean conditions with chemically pure ingredients and are simple enough to model computationally or to describe analytically. The experiment is conducted in air on top of a dimension heater-cooler. When the sample temperature passes the polymer's glass transition temperature, Tg, it starts to behave like a viscous fluid. The de-wetting process can now be observed. The speed of the process is temperature dependent. De-wetting always involves the formation of holes in the film, which grow and join, leaving linear structures which finally rupture and form droplets. Over much longer timescales, these droplets could diffuse and join and finally form one single drop. For practical purposes, the droplet stage is the final stage. Where the processes differ is how the holes initially form. The formation of the holes implies a breaking of the symmetry of the film. In the case of heterogeneous nucleation, impurities in the film or substrate are the nucleation sites for holes, and holes form simultaneously and therefore have In the case of heterogeneous nucleation, impurities in the film or substrate are the nucleation sites for holes, and holes form simultaneously and therefore have similar sizes later. Thermal nucleation only occurs on very thin, like a few nanometer, films and are caused by thermal fluctuations in the film. Heat is random motion. In a very thin film, this motion does not always average out, and holes can spontaneously form. Once the holes are there, they grow. Spinodal de-wetting occurs when the heated film forms surface waves, which amplify over time if the interface potentials favor that, until the wave amplitude exceeds the film thickness. Because of this mechanism, one can see waves early in the process and linearly grouped holes in the later stage. The collaborators, who also made the sample, are the groups of Professor Ralf Seemann and Professor Karin Jacobs, their husband and wife, and both at the Universität des Saarlandes in Germany. Both are long-term Vico Bruker AFM customers and excellent references. They have spent some academic time in Santa Barbara. Professor Jacobs is an early bioscope catalyst customer. Professor Seemann was the first dimension icon customer. Now, let's move to the next slide. From the beginning, we are heating the polymer film on the silicon surface to 55 degrees initially, and we see the holes appearing. Eventually the process slows down as it comes closer to thermal equilibrium, and we increase the temperature to speed it up again. Here is 65 degrees C. And here is 75. You can see in the movie how good our control over the process is through the control of temperature, and how critical in general controlling the process is to observing dynamic processes in an AFM. On the right hand side, the details of this movie. It was taken on a dimension fast scan system using the dimension heater cooler, a broadband A probe. It was imaged in tapping mode in air. The line rate was 23 lines per second with a tip velocity of 70 micron per second. We imaged at a resolution of 1024 horizontally by 512 lines. The whole movie consists of 340 frames taken over 2 hours. This works out to 22 seconds per frame. The short description here is in the bottom. In situ recording of a 5 nanometer thick polystyrene film with a molecular weight of 4.2 kilograms per mole, de-wetting a hydrophobic silicon wafer at 55, 65 and 75 degrees C. The data was acquired by Matthias Lessel and Karin Jacobs at the Universität des Saarlandes and by myself. Finally, we come to some conclusions. In the top we have the academic conclusions, in the bottom the product conclusions. The individual appearance of the holes identifies the process of hole formation as thermal nucleation. How can we tell? Well, the holes are appearing individually, one at a time. It almost appears like they are bubbling up, and so this is indicative of the thermal nucleation process. It's random. However, the collaborator, while we did this measurement, also noticed the pattern of smaller all similar sized depressions without complete hole formation, which may hint at a concurrent spinodal effect. This is still under investigation. They appear later in the process and are soon overwhelmed by the holes caused by the thermal nucleation. And so they had not been previously time resolved on the sample. From a product point of view, the dynamics experiment was enabled by the unique combination of fast scanning and sample temperature control, using the dimension heater cooler. Control of different sample environmental parameters is made easy to implement and in many cases enabled by the tip scanning open platform geometry of the dimension fast scan system. Let's look at this in a little more detail. The capability of the dimension fast scan to be combined with heating and cooling is unique among high-speed or small cantilever AFM, including academic systems. The tip scanning design much favors or even enables such combinations. Sample scanning systems need to limit sample mass to retain good performance. For standard AFM, for example the multimode, this still allowed the integration of a heater. Faster AFMs need to further restrict the moving mass. The fastest sample scanning AFM with feedback, the one from Professor Ando in Japan, use a 1 mm mica disc directly glued to the scanner for this reason. Scanning the mass of a sample heater plus the required heat isolation from the scanner is somewhere between difficult and impossible at high scan speeds. A fast tip scanning AFM is entirely unaffected by this problem. Looking further, most other methods of triggering dynamic processes can also benefit from the tip scanning design and open platform of the dimension fast scan, and it will be much easier to develop them, or for technically savvy labs, even to invent and integrate such setups themselves. This concludes our session on the thermally induced polymer film de-wetting, imaged by the dimension fast scan and the dimension heater cooler. I hope you enjoyed it and tune in next time. Next time we'll be live. Bye bye.